Okay, hey everybody. So I just started the recording. Today we are doing topic 41, which is actually in Canvas titled Deep Neural Networks, which is true. But I like to use this study to talk more about the tuning of neural networks. And I know the next topic is called tuning neural networks, but I'm going to talk about different things next week as well. So what we're going to talk about today, we're going to break it up to kind of two parts. First, just some of the different hyperparameters that you can tune in a neural network. So all of these, let me zoom in a bit. And then we're also going to get into convolutional layers. And that is the thing that's actually in the appendix of our image classification section. I really do recommend that if you're doing the image classification project, which I think 3 of you in this cohort are, if you're doing that, I really, really recommend that you use these convolutional layers, which I'll talk about in a bit. Yes, they're in the appendix, so technically you don't have to, but if you're doing images, you should try to use convolutional layers. And it's really just a matter of like changing the kind of layer that you're using. You'll see what I mean later on. Cool. So we're going to talk about tuning neural networks. Now, in my experience, especially if you're new to neural networks, tuning neural networks is not an easy thing. It's not the same as like for a lot of the machine learning models we were talking about last phase, where let's say you have overfitting. Okay, I know some for like the tree-based things, maybe I like adjust the max depth. Or for other models, I can like adjust regularization. It's a little less straightforward than that just because of the black box nature of neural networks. Next week for topic 42, I'll actually show you all like how to implement something like grid search for neural networks, but today we'll just talk about the different things that you can tune. So table of contents on the side over here, but let's start with nodes and layers. So as you saw from yesterday, and I'm going to pull up the neural network that we actually played with yesterday, nodes and layers. So each one of these I'm adding is a layer, which as you can see, like pretty easy. If you want to add layers, you pretty much just copy and paste and you have more layers. Another thing that I said yesterday that you kind of arbitrarily pick is the number of nodes or the number of perceptron units per layer. And that's the number over here. So generally, the more nodes that you have and the more layers that you have, the more granularity you will get in your training boundary, just because you're doing more operations on your parameters. So if we go through this, first, number of hidden layers. For some problems, you can start with just 1 or 2 hidden layers. It'll work just fine. The more complex your problem is, you can ramp up the number of hidden layers that you have until your model starts to overfit. So something that's very common to see if you have just a lot of hidden layers, where maybe in cases you don't need to have that many hidden layers, you get overfitting. And that's something that you'll actually see when you look at your training history graphs. So I talked about this yesterday a little bit, but if you start to see like the test start to diverge from your train, clear sign of overfitting, you can kind of cut off your training at some point. So for very complex tasks like image classification without convolutional layers, and again, I'm going to talk about convolutional layers towards the end of today, you will need dozens of layers. So the more complex the problem is, the more layers you would add, the more nodes you might have within each layer as well. And the number of parameters that you'll have in a model will like increase more than exponentially too. So another thing that you can tune, again, this is I feel like the number of neurons per layer is a lot more arbitrary. The number of neurons per layer, basically more neurons, more granularity. However, something that you have to put the correct number for is the number of neurons for your input and output layers. So I mentioned yesterday, this problem, we had 8 features in our data. So the input dimension is 8. So always make sure that you have that right. If you don't have that right number, it'll tell you there's some sort of like feature shape mismatch or something. Another thing to note is for your output layer, we were doing binary classification. So the output layer was just a 1. Later in this notebook, or not this notebook, this other notebook, I'm going to go through a multi-class problem. And you'll see in a multi-class problem, I'm going through a 10-class classification problem. The number of nodes you have in your output class in your output layer should be 10, or equivalent to the number of classes that you have, as long as it's more than binary. Cool. So input dimensions are determined by a number of columns, and your output layer for classification has 1 node with a sigmoid activation function. That is for binary classification. And then for hidden dense layers, a common practice is to create a funnel with fewer and fewer neurons per layer. And this is actually more specifically for hidden dense layers, like what we talked about yesterday. I started with 20, went down to 12. If I added another one, maybe I make it, I don't know, 5, or I can even like increase all of these numbers from like 100, 50, 25, all arbitrary. Cool. In general, you'll get more bang for your buck by adding on more layers versus adding more neurons. That makes sense because in one layer, you have a lot of neurons. Any questions about how nodes and layers work for your task?
Just a quick question. Does the dimensions of the data going in have to match data coming out? I'm not sure if that makes any sense. I just remember like going through the lab and I was kind of confused if you have like a multi-class problem and it's like a so the input target versus the output target, do those need to match? Or can
Gotcha.
I mean, obviously it wouldn't make any sense, but why you would do that, but like, yeah.
Yeah, it doesn't have to match.
Okay.
This has to, the main thing that you have to look out for is this has to match the number of features that you have. So the shape of your input data has to always be the same, which makes sense because between your trainer and your test set, you wouldn't have different number of columns. You'll have different number of rows, which is fine, but number of columns should always be consistent. And then, yeah, your output layer, the number of nodes you have in your output layer, again, depends on the kind of task that you're doing. Really, I think the main thing of the things that we've seen so far is multi-class classification is the only one where you wouldn't have a single node. Cool. Any other questions? All right. So the next thing is activation functions. And where do activation functions come in again? Actually, let me grab our notebook from yesterday. Activation functions come in after the summation within each node. So at the end of every node, or kind of like, yeah, the last step that is done within each node is an activation function. So there's an activation function happening at these x's over here before it gets aggregated into either the next layer or the output. Now, within a layer, and this is something that is within Keras, every node within a single layer has the same activation function. Now, for hidden layers, you can pretty much pick and choose different activation functions. If you're picking and choosing different activation functions, the effect of the activation functions could change like how your model learns, but most activation functions should work for hidden layers, as well as your input layer. The main activation function that you have to take note of is your output activation function. So going back to here, actually, let me talk about this first. So I talked about yesterday, we had sigmoid activation function for our binary classification problem. And that's because it coerces your values to be between 0 and 1. Later, we're going to do a multi-class classification problem. And usually you use softmax activation because it produces a non-negative vector that sums to 1. So in our 10 class problem, the output is actually going to be a vector of 10 different numbers corresponding to the probability of that data point belonging in each class. And then for regression problems, which we actually don't have an example of over here, but you could always do a regression problem if you wanted to. You can either do a linear activation function, and linear activation function really just means you're adding it together, or ReLU activation, because ReLU activation function, I'm going to talk about these briefly later. You can see that this part, as long as it is positive, is pretty much the same as a linear function. Cool. So in terms of activation functions for hidden layers, there's a lot of detail that goes into like why you would want to choose different activation functions over others. I will say that at this point, you can probably just run some sort of grid search to see which one ends up working better for your model's architecture. I did link a couple towards data science articles here if you wanted to read more. Typically, the two most common activation functions that are used within hidden layers, currently ReLU performs very, very well. And then the other one that is used especially for RNNs, which we'll talk about next week, that's like the forecasting neural network, hyperbolic tangent, the TANH activation function is the one that's very commonly used in those kinds of neural networks. But usually ReLU performs well. You can actually test, I'll show you all again next week. You can test a bunch of different ones to see which one works best. Cool. So we're going to get into a little bit of like the math of activation functions as we talk about this. So typically sigmoids, if it's not for the output layer for binary classification, it is not often used in hidden layers because it has a small maximum derivative value and thus only propagates a small amount of error each time, leading to slow learning. So what does that mean? If you remember when we talked about calculus like 2 phases ago, the derivative is sort of like the slope of a function. So you can see here, for a sigmoid function, the maximum slope, or wherever it's the steepest, is not as steep as some of these other functions. So because the sigmoid's maximum slope is not too great, the idea here is that when you're using this backpropagation process, which again, we don't really have time to get into a lot of detail with, because the slope is not very great, you usually have much slower learning. So less of the error gets propagated back. So therefore, ReLU, which usually has like a very linear derivative, much faster learning. So this small derivative slow learning issue is known as the vanishing gradient problem. This is also very similar for tanh, because tanh also kind of has like a cap on the maximum derivative. So that's why you don't typically see it work as well or as quickly as a ReLU activation function. So ReLU generally works well because its gradient is always 1 as long as the input is positive, and negative inputs going to 0 can actually make your network lighter. So imagine after aggregating all of your weights and biases, if your aggregation is 0 or less, that node will actually be essentially taken out, or it won't really be considered because it has an output of 0. So it can actually help to speed up some computation as well as making your neural network just lighter. Cool. Any questions with regards to activation functions? This is, I think, one of the more abstract parts of neural networks at this point. For us and for this project, I think it's good enough to just try a couple. I'll show you all in that grid search process next week. Just try a couple and see how it affects your model. Cool. All right, so from activation functions, next let's talk about loss functions. So where do loss functions come in again? Loss functions come in when you do your model compile step. And remember, for neural networks, it's actually optimizing for reducing your loss function as much as possible, not optimizing for a specific metric. So when you're doing grid search, you could optimize for accuracy, F1, recall, but for a neural network, it actually looks at your loss function, which sometimes can be the same as your metric, as we'll see in a little bit. But this is what's being optimized for. So loss functions are akin to the cost functions we were trying to minimize in gradient descent. So for example, RMSE was our cost function for linear regression. We were using Gini or entropy when we were looking at any tree model. So for regression problems, Keras has mean squared error or mean absolute error as a loss function. There's also mean squared log error if your target has potential outliers. So it basically reduces the amount of error for your large outliers. For binary classification, the loss function is actually binary cross entropy. It's kind of a similar calculation as the tree entropy. And then for multi-class problems is categorical cross entropy. And basically, you're trying to maximize purity within each classification boundary. So if you remember from yesterday, we used binary cross entropy. And later, we'll see an example where we are using categorical cross entropy. So loss function is very, very task dependent. Cool. Questions about that? Okay, so next we have optimizers, and I have like a couple like really good articles that go into much more detail than what I'm going to talk about. But different optimizers just kind of specify the different kind of methods or paths that your neural network can take to find optimal values. So experimentally, ADAM, which stands for Adaptive Moment Estimation, is a good one to use. And I've linked a resource on reading more about ADAM if you like. So quick optimizer summary, I would say that these are the three, at least out of the ones that I've seen, three of the most common optimizers. And optimizers also come in at the compile step. So there's one called RMS prop, And RMS prop basically maintains per parameter learning rates that are adapted based on the average of recent weight updates. So this does well on non-stationary problems. So basically, if you see that one parameter has started to like stabilize itself, it'll automatically reduce the learning rate so that instead of overshooting its optimum, it can sort of like slowly try and approach that optimal value. So it's making those adjustments. AdaGrad does that as well. That improves performance of problems with sparse gradients. So if you have very sparse data, so for example, natural language processing, we saw that if you do like TF-IDF, you end up with a very, very sparse matrix. That's an example where AdaGrad could perform well. Computer vision problems as well. We're actually going to see image data right after this. AdaGrad also tends to do pretty well in those instances. And then finally, Atom is kind of like the happy medium between the two. So instead of adapting the parameter learning rates based on the average first moment, which is the mean of the last few updates, Atom also makes use of the variance of the gradient. So it's basically using more information to decide how to change this learning rate. Cool. Questions about optimizer. I realize that optimizers is also kind of abstract.
Okay, so
Yeah.
RMS prop would be used for the time series, undifferenced and I guess modified data in this case. Yeah,
you can. I actually think you could use either of these optimizers for any problem. It's just which ones work better. Yeah, I would imagine that RMS props works better than something like AdaGrad in a time series problem.
Okay, thank you.
You're welcome. And optimizers is actually something that you can also tune as a hyperparameter in your like grid search that I'll show you all next week. So if you're not sure which one to pick, you can try them all. All right, so next there's learning rate. And learning rate is something that you can define when you compile your model with the optimizer. So if you wanted to, you could actually add a learning rate parameter in this compile step. You can also add learning rates within each layer if you want. So optimizers usually change up the learning rates anyways. So this is just the initial learning rate. If you set it to low, training will eventually converge, but very, very slowly. If you set it to high, it might actually diverge and like take a very long time as well, but because it keeps overshooting its optimum. And if you set it slightly too high, same thing, it'll converge at first, but maybe miss the local optima. So playing with learning rates, you actually don't really have to define learning rates at any point with a neural network. There are some default values there for you, but if you feel like your neural network is taking too long to learn parameters, you might want to adjust that, but you don't have to as well. Okay, so learning rate kind of like an optional thing that you can play around with, I would say, after you get more and more experience with implementing neural networks. Questions about that? Okay, so the last thing I want to talk about is regularization. So something that we mentioned yesterday is because neural networks are so complex and there's so many parameters, like how with this problem over here, this 8-feature problem, we already have 445 parameters being trained. There is a high propensity to overfit. So because of that, there are different ways that you can actually regularize. So you can first, actually for some context, as a neural network learns, neuron weights can tend to settle into their context within the network. So one way of thinking about this is if I am training something to classify images of, let's say, cats and dogs. If I was training something to do cats and dogs, maybe some of the parameters will be focused on, okay, what is their fur color? Maybe some other ones will be focused on, all right, what about the like structure of the pet's head or something like that. So different weights will actually sort of settle into learning specific parts of whatever it is that you're trying to classify or regress or predict. So weights of neurons are tuned for specific features, providing some specialization. So neighboring neurons might become too reliant on this specialization, which if taken too far, can result in a fragile model too specialized to the training data. So one example of this, I forgot where I read this, but someone tried to build like a model classifying like dogs versus wolves or something like that. And basically they're like, okay, this classification model performs great. However, in looking into like the parameter values and what was being trained, they actually realized that instead of focusing on, things like maybe the size or the kind of fur or like different, like, I don't know, characteristics of wolves and dogs, it actually started to look at things like, all right, if it is indoors, it's more likely to be a dog. If it is in like the wilderness, it's more likely to be a wolf. So things like that can lead to, well, they do lead to overfitting because you're focusing on something that is maybe too specific to the training data. So this reliance on context for a neuron during training is referred to as complex co-adaptations. I haven't really been asked, I've never really been asked about complex co-adaptations, but it's something that's good to know. So different methods of doing regularization. Within any hidden layer, you can actually introduce regularization. It works very similar to, if you remember, like when we did our ridge and lasso, actually works very similar to that. So you can actually add L1 or L2 regularization within your layer. So if you click here, I believe you add like regularization. Is it going to autocomplete? I haven't run this model, but yeah, you can add regularization or something similar to that and tell it what kind of regularization you want. You can also add a dropout layer. And dropout layer is something I'm going to talk about in a little bit, but also not technically regularization, but you can also introduce something known as early stopping so that your model doesn't overtrain. So if you remember what I talked about yesterday, where let's just imagine that in this scenario, we see our test metrics start to deprove after a certain point. So instead of this, let's just say we end up getting something that looks more like this. So it peaks over here and then starts to decrease in validation accuracy. So something that you can introduce is something known as early stopping. And I'll show you all a code snippet for that in a bit, where it says, okay, after a certain number of epochs, if my validation metric doesn't improve, I'll just cut off training right over there. So that, because if you let something keep training, the training loss and accuracy will always get better and better, but your test accuracy may not. So to show you all some code for that, dropout. So dropout is a technique where randomly selected neurons are just going to be ignored during training, and they are dropped out randomly, therefore the Thanos reference. So this means that their contribution to the activation of downstream neurons is temporarily removed to the forward pass, and any weight updates are not applied to the neuron on the backward pass. So literally, that means that if I have 100 neurons in one layer, feeding into the next layer that has maybe like another 100 neurons, between the two, if you put a dropout layer, it's only going to consider 50 of the neurons if you set dropout to be 0.5. So a dropout layer looks something like this. All you have to do is model.add dropout, and you specify a ratio of how many of the neurons you want to ignore. And then the other thing I was talking about, early stopping. So you'll first have to instantiate an early stopping object, and you give it some sort of patience value. So this patience value that you can choose really depends on the performance of your model first. I would actually say run your model maybe a couple times without early stopping, or set your patience to be very high first, and then you can adjust this. As you can see here, with our neural network from yesterday, it is very, very unstable. So maybe you want to set your patience to be something like, I don't know, 2 or 3, so that it can kind of capture an optimal testing value or something like that. That's something you can play around with. Because there's also a chance that if you set your patience to be too low, if maybe in like epochs between epochs 30 to 40, nothing really improves, it might stop there. So you really got to play around with this patience value, but it does save you a lot of computational time and power if you introduce early stopping. Not technically regularization, but it's a way to stop your model from overtraining itself. All right, so those are all the main things that you would think about when compiling or deciding on your model architecture. Before I talk about images specifically, does anyone have any questions? Okay, so let's talk about convolutional layers. If you're doing anything in like 2D or in a tensor 3D with colored images, convolutional layers are actually really, really good for that. And you'll sort of see why as we talk about it. So convolutional layers, any neural network with a convolutional layer is a CNN, which stands for convolutional neural network, and they're mainly used for image recognition or classification. They can be used for video analysis, NLP as well, and speech recognition. So in thinking about how convolutional layers are helpful, think about how do our brains see an image. So if we might see a fluffy tail, wet nose, flappy ears, and a good boy, and conclude that we're probably seeing a dog, especially when looking at this like creepy collage of images. There's not one singular thing about a dog that our brain recognizes as a dog, but so it's more of an amalgamation of different patterns and features that allow us to make that probable guess of like, okay, that's probably not a dog, that's probably a dog. How do computers see images? Basically, we kind of like touched on this slightly when we talked about linear algebra, but computers see images as vectors, matrices, tensors. So to computers, color images are a 3D object comprised of 3 matrices, one for each primary color that can be combined in varying intensities to create different colors. So it's a tensor of 3 matrices. You get a blue, a green, and a red matrix, and they're kind of layered on top of each other to form a color image. Sometimes, I forget what specific data type it is, what image file type it is, but sometimes you get a 4th layer, which determines like, I think the transparency of the image. So if you see any that has 4 layers in your tensor, that's probably what it is. But typically you just have 3 layers of a red, green, and blue. So each element in the matrix represents the location of a pixel and contains a number between 0 and 255, which indicates the intensity of the corresponding primary color in that pixel. So this is a super zoomed in. This is literally just looking at 9 pixels in this image, I guess. I don't know how accurate this is, but in those 9 pixels, you have these values of blue, green, and red. Cool. Any questions about the representation of images as numbers? Okay, so convolutions. To convolve means to roll together. CNNs basically make use of linear algebra to identify patterns using pixel values. By taking a small matrix like this and moving it across an image and multiplying them together every time it moves, our network can mathematically identify patterns in these images. So this small matrix is known as a kernel or a filter, and each one is designed to identify a particular pattern in an image. So things like images, shapes, color combinations, textures, things like that. So if this is our base image, and let's just imagine we just have like one matrix representing our image for now, we're going to get this kernel or filter, and it's usually much smaller than your original image, and it's going to kind of mask itself across the entire image. And what it's doing is, you see it starts from the top left and ends at the bottom right. Every 9 squares, it's going to do an element-wise multiplication. So you can see here, there are just these like arbitrary numbers of like -1, -2, -1, a row of zeros, 1, 2, 1. It's going to take that element-wise, multiply whatever it is overlapping, and you end up with one number per space where it's mapping. And so this means something as well. But any questions about what's going on over here? This process. And this is what's powerful about convolutional layers, because it's still looking at the image as like some sort of 2D object, which is much more helpful. If anyone has gone to the neural network lab with the first image neural network lab, you're actually taking the image and you're actually turning it into one super long vector. So you don't really get that 2D representation that convolutional layers allow you to do. Any questions about what's going on over here? Okay, so when this filter is rolled over an image, the resulting matrix, which is this one over here, is called a feature map. It's literally a map of where each pattern of feature is in the image. So elements with higher values indicate the presence of a pattern that the filter is looking for. Now, the values of the filter, that's something that you actually don't have to worry about, because these will be adjusted during backpropagation. So you actually don't have to specify, oh, I want to look for edges this layer, or I want to look for colors this layer. You don't have to do anything like that. So some things to consider when you're looking at convolutional layers. First, padding. So you see how this is a 3x3 matrix, and then this, I guess, is a 5x5 matrix. Sometimes it's convenient to pad the input volume with zeros around the border, zeros along the side here. This helps with detecting patterns at the edge of the image, because if without padding, you might underrepresent something that's happening towards the edges of an image. Next, there is stride, which is the number of pixels to shift the filter on each roll. So this is actually a stride of 1 because it's shifting by 1 each time. You can set a stride of 2. So every time it will shift by 2 units. The larger the stride, the smaller the feature map will be, which could be good for computation, but we do lose more information because we're not considering each pixel as many times. So these are things that you can tune in your convolutional layers. So typically with convolutional layers, you have another kind of layer that always comes with convolutional layers, known as pooling layers. So with pooling layers, after convolutional layer, the feature maps are fed into some sort of max pool layer. It doesn't have to be max pool. I'll talk about that later. Like convolutions, this method is usually applied one patch at a time, usually 2x2. And what's happening is, let's just say that this is the feature map that we get. So this is the feature map that we get after doing some sort of like convolutional whatever. Max pooling, which is a kind of pooling layer, will take the largest value from a patch of an image and place it in a new matrix next to max value from other patches. So let's just say that this is our filter map. We're max pooling with a 2x2 filter with a stride of 2. That means that first, actually, let me draw it out. First, it'll look at this slice, then it'll look at this, then it'll look at this, then it'll look at this, because it's shifting 2 every time. And this is also something you can adjust if you'd like. And what it's doing, max pooling, is it's just taking the maximum value from each, what do you call that? Like from each square, let's just say that. So that's why it's taking 6, it's taking 8, it's taking 3, it's taking 4, because these are the max values from each of these overlapping parts. So that's called max pooling. So this process will basically result in a new feature map with reduced dimensionality that is then passed into another convolution layer to continue the pattern finding process. So these steps are repeated until they are passed to a fully connected layer that proceeds to classify the image using the identified patterns. So other methods exist. So you don't necessarily always have to take the max. You can also take an average. Different ones have different effect. I feel like at this stage, you could just try different ones. Max pooling is used a little bit more often, just because when you have the maximum value of something, you know that, okay, that's an indication that a certain pattern is there, rather than taking an average, but both will essentially do similar things. Cool. So in convolutional layers and pooling layers, you're dealing with your information still in 2D, but when you want to do some sort of prediction like classification or regression, you usually want your output is like a single number or like a single vector if you're doing multi-class. So some element of, you basically have to flatten your data at some point. So the last kind of layer we're going to talk about is a flattening layer. So once a neural network has collected a series of patterns that an image contains, it is ready to make a guess as to what the image is. So in order to do so, it starts by flattening the 2D matrix into a 1D vector so that it can be passed into a normal densely connected layer for classification. I'll show you all an example of a convolutional neural network, so that'll make a bit more sense. Then using this vector, one or many densely connected layers will make a prediction as to what this image is. So let's see some examples, but before that, any questions about any of these new 2D layers we're talking about?
The stride is mainly used just to kind of like speed up the process, or what?
Yeah.
Okay.
That's right.
All right.
Anything else? Cool. All right, so let's build a very, very simple CNN. You'll see that because this is for the purpose of demonstration, it's not going to perform well, but I'll show you all a resource later that will help. Okay, so things that we're importing. I'm actually using this CFAR10 data set. I'll show you all some examples later, but it's basically an image data set with 10 different classes of images. And then also, I'll show you all what 2 categorical is as well. And then all of these we know already. So I'm just going to run this cell real quick. This is just an example of what this data set looks like. They're very, very small images, but you can sort of see that, all right, vaguely, I think that's a frog. You have like some trucks, cars, horse, bird, boat, 10 different classes of images. I also forget what exactly they are. Some pre-processing things to note. You can see that here, my training set, or actually, yeah, all of my image data exists in 32 by 32 by 3. So basically, to create this color image, there are 3 layers of 32 by 32 matrices that just, talk about the intensity about that indicate the intensity of the red, green, and blue values. And then in my train set, I have 50,000 images. In my test set, I have 10,000. Same for my Y. As you can see here, when we were doing our scikit-learn modeling, we usually only have one column for our Y value. And that's actually the same when we are doing binary classification. But because of the nature of the loss function for neural networks doing multi-class classification, we actually have to convert this into pretty much like dummy variables or one-hot encoding. So you end up with a like a matrix showing. Actually, let me see if I can output this. So Y train, yeah, oh, basically like this. So this is class number 10 out of 10 as an example. This will be class number 2 out of 10. So your target variable has to be in this form if you're doing multi-class problems. Cool. So because our Y is in a matrix, instead of doing value counts, we're just going to do a dot sum. So you can see it was very, very balanced. We have 5,000 data points of each class. Okay, so let's get into our first CNN. So typically what you have is you have these convolutional blocks where it is a few convolutional layers followed by some sort of pooling layer. So right now I'm doing this. I have 2 convolutional blocks. This very first one, or actually both of them, have 1 convolutional layer and 1 pooling layer. In the very first one, I just have to tell it the input shape. So very similar to what we had with the numerical example, where you give it the input dimensions. Here you just tell it what the shape of the image is, and it's 32 by 3. If it's a black and white image, it should be, I want to say it's 32 by 32 by 1. If it's a grayscale or black and white image, you'll probably see an example of that at some point. But we have these 2 convolutional blocks. They're going to do this. And then after we're done with our 2D layers, we just add this flatten layer. And then we can add as many dense layers as you want to afterwards. And then finally, we have our output layer. So our output layer, because we have 10 classes, our output layer must have 10 nodes. And that actually means that you're outputting a vector of length 10. And then the activation, this is just typical for multi-class problems, that the activation is softmax. When you're compiling the model, you're using categorical cross entropy. That's also another typical one for multi-class problems. Optimizer here, just to show that I'm using a different one, I'm using SGD. And in terms of metrics, I can keep track of accuracy. If I wanted to, I can add on F1, recall, so on and so forth. So if you take a look at this model, the number of parameters that we have is 57,482. So we have this number of parameters that are being tuned throughout the backpropagation process, which is why CNNs take a very, very long time to train. I can just run this because you can, but you can see here, it's not going to perform very well because we only have, I'm only doing it for 5 epochs, but I think it's just cool to see the progress of the training. So if I run this, you can actually keep track and see, well, ETA, but also you can see it undergo its training. And by the way, here I'm doing a batch size of 500. So batch size of 500 in a train set of 50,000, right? Hold on, let me double check. Yeah, with 50,000, that's why we have 100 batches. And that's why you get out of 100 there. Cool. So while this is training, I already ran this earlier. We end up with not great results because we're only doing it for 5 epochs. Typically with neural networks, actually my other cohort that finished this project recently, with the provided data set for image classification, people were running about 100 to 400 epochs to see like meaningful results. So set your expectations. So with that, you can see that the training is happening. I can evaluate my train and test results. You can see at this point, not great, but that's only because we don't have relatively don't have a lot of layers. And yeah, we end up with like pretty much like random guessing, 10% accuracy. We can plot the same kind of graphs as we did last time as well. Just to show you all the kind of network that can be done on this data set. And also this data set is a little harder because you have 10 different classes. There's this article over here that actually walks through iteratively running a bunch of different kinds of neural networks and looking at their overall results. So for this final model in this long article, they ended up with a accuracy of 73%. And with 73%, this was their model. So you can actually do it in a function as well. For those of you who like to write functions, you can do this, but you can see here they have 1, 2, 3 convolutional blocks, each with 2 convolutional layers and a pooling layer. And then they flatten and they have their 2 dense layers. Now, I know I said that for dense layers, you typically like to see that funnel shape, but for convolutional layers, I actually personally don't really know why either. I have seen in a lot of work examples that it kind of goes the opposite direction, where it increases in the number of nodes per block. I haven't looked into why myself, but that's what seems to work. I've linked this article here as well. I've linked it over here. And this is a great one just to see like all of the different things that you can think of including or different things to try when you're doing a CNN. But cool. Any questions at this point? All right. Well, that's it for today. Next week on Tuesday, we're going to talk about these things. So we're going to talk about transfer learning. We're going to go through like on a kind of high level recurrent neural networks and how they work. We're going to talk about grid search for neural networks, as well as how you can save your models, because it's not as simple as doing like a dot pickle, or not dot pickle, but it's not as simple as pickling your model. So we'll talk about that next week. On Wednesday, so a week from today, that's when I'll officially be kicking off the project. But all of you, as I said, you can get started on your projects, especially those of you who are working on the projects that are not the neural network project. One more thing that I keep meaning to mention. Oh, yeah. If you look at our calendar, I set the presentation date for our project to be on the 17th of November. So just take note, this is the day that we'll do our project presentations. Yeah, just so that we have a little bit of a break between presenting our project and kicking off the capstone. All right, does anyone have any questions at this point? Cool. If there are no questions, if we haven't talked about the project enough, please schedule a one-on-one with me so we can talk about it. Any other questions that you have for me, just let me know. Let me know. I'll see you all at your upcoming one-on-ones or next week at study group. Right. Bye, everybody. Have a good night.
Bye. Thank you.
Bye, everyone. Have a great night.